Welcome to our exploration of Einstein's theory of relativity, one of the most revolutionary scientific theories ever developed. Albert Einstein published his special theory of relativity in 1905, and then the general theory of relativity in 1915, completely transforming our understanding of space, time, and gravity. Before Einstein, our understanding of the universe was based on Newtonian mechanics and classical physics. In this classical view, space and time were separate, absolute entities that were the same for all observers. For example, if two events happened at the same time for one observer, they would happen at the same time for all observers, regardless of their motion. Einstein's special theory of relativity introduced two revolutionary concepts. First, the laws of physics are the same for all observers moving at constant speeds relative to each other. Second, the speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. These principles lead to several mind-bending consequences. One of the most fascinating consequences is time dilation. Time passes slower for objects in motion relative to an observer. Imagine a clock on a spaceship moving at high speed. To a stationary observer watching the spaceship pass by, the clock would appear to tick slower than their own clock. This is described by the time dilation formula. Delta t prime equals delta t divided by the square root of 1 minus v squared over c squared. Where delta t is the time measured by a stationary observer, delta t prime is the time measured by the moving observer, v is the relative velocity between the observers, and c is the speed of light. Another consequence is length contraction. Objects in motion appear to be shortened in the direction of their motion. For example, a moving spaceship would appear shorter to a stationary observer than it would to someone traveling with the spaceship. This is described by the length contraction formula. L prime equals L times the square root of 1 minus v squared over c squared. Where L is the proper length, the length in the object's rest frame, L prime is the contracted length observed in a moving frame, v is the relative velocity between the frames, and c is the speed of light. Perhaps the most famous equation from Einstein's theory is the mass-energy equivalence, E equals mc squared. This equation tells us that mass and energy are equivalent and interchangeable. Energy has mass, and mass represents energy. This principle is what enables nuclear power and nuclear weapons to work. A small amount of mass can be converted into an enormous amount of energy, as the speed of light squared is a very large number. 10 years after special relativity, Einstein published his general theory of relativity. This theory extends special relativity to include gravity. The key insight of general relativity is that gravity is not a force, but rather a curvature of space-time caused by mass and energy. Massive objects like stars and planets warp the fabric of space-time around them, and this warping is what we experience as gravity. Objects moving through space follow the shortest path in this curved space-time, which is called a geodesic. This is described by Einstein's field equations. G subscript mu nu equals 8 pi g over c to the fourth power times t subscript mu nu. In simpler terms, these equations tell us how matter and energy curve spacetime, and how this curvature affects the movement of matter and energy. Einstein's theories have been confirmed by numerous experiments. Special relativity has been confirmed by particle accelerators, where particles moving at near light speed behave exactly as predicted by the theory. General relativity explained the anomalous precession of Mercury's orbit, which Newtonian physics couldn't account for. It also predicted that light would bend around massive objects due to the curvature of spacetime. This was confirmed during a solar eclipse in 1919, making Einstein world-famous overnight. Today, GPS satellites must account for both special and general relativistic effects to maintain their accuracy, providing a practical application of Einstein's theories in our everyday lives. Einstein's theories of relativity completely transformed our understanding of the universe. They showed us that space and time are not absolute, but relative, that mass and energy are equivalent, and that gravity is a curvature of space-time. These theories continue to be essential in modern physics and have led to many technological applications. Most importantly, they remind us that our common-sense understanding of the world sometimes needs to be revised when we look at the universe more deeply.